Hello and welcome to another video. In this problem, we're going to be working on largest submatrix with rearrangements. And in the problem, you're given a binary matrix of size m times n, and you're allowed to rearrange the columns of the matrix in any order. Return the area of the largest submatrix within the matrix where every element of the submatrix is 1 after you reorder the columns optimally. So you're allowed to move the columns around. So in this case, you would want to move the columns around to have this pair of ones and this pair of ones together. So here you would get an area of 4. In this one, you want to move all the ones together, so there's a bunch of ways to do it, but essentially here you would get an area of 3. And we can do this last one. So for this last one, we have 1, 1, 0. And we also have 1, 0, 1. So what you'd want to do is you'd want to swap these two columns. Actually, even if you swap these two columns, it still wouldn't matter because you still wouldn't get a bigger area. So the biggest area you can actually have is this, or this, or there's like a few of them. But essentially, even if you swapped these columns around, you can never get a 4x4 or like anything bigger than a 1x2. So the answer here is 2. And that's kind of what they tell you. You must rearrange the entire columns. There's no way to make a submatrix with larger area than 2. So we're actually going to focus on how to do this. And the first thing to notice is the constraints are m times n is 10 to the 5th. So if that means that we're looking for like a linear or an n log n approach, and anything fast, anything slower is not going to work, right? So we want to have like a 1 pass or some kind of maybe like sorting some stuff, but we can't have anything slower than that. So what we're going to do is we're actually going to figure out for each column, like what's the biggest rectangle we can make with that column. And the way we're going to do that is we're actually going to write, instead of storing it like this, it's kind of useless, we are going to do it another way. And so I have an example here where we have 5 different columns and we have a bunch of numbers. And these ones are okay, but really what we want to figure out is like, for these ones, how far does the rectangle go with these ones, right? Like if I have a 1 here and 1 here, can I make a rectangle, and how do I know? So the way we're going to do this is, instead of storing these as ones, what we're going to do is we're going to go down the column, and for every consecutive one, we will actually add a 1. And then every time there's 0, we'll just reset it. So essentially here it'll be like 1, then we will change this to 2, and we'll change this to 3, right? Because we have a consecutive one. And this tells us that if we're at this location here, there are 3 ones in a row, right? We know that from one number. And that's going to help us a lot, as opposed to a bunch of ones where like we'd have to count it up. So let's do that as well here. So we have 1, 2, and 1, 2. And then this is 1, 2. Let's actually just clean it up a little bit. So this is just going to be 1, 2, 3, 4, 5. And right, we have a lot more information now. Like we know for this 5, we know that there are 5 ones in a row here that we can use to make a rectangle. So we're basically getting a lot more information just from one number now without having to like loop through anything. So we have 1, and then we have 1, 2, 3. Okay. Now basically we're going to focus on, for each row, we're going to say, okay, well, let's say the rectangle we have, the bottom right corner of the rectangle, that's probably a good way to do it. The bottom right corner of the rectangle, so let's say we have a rectangle, is this one here. And then what's the biggest rectangle we can build that way? Right? So let's figure that out. Now also notice for this row, we're also going to want to do one more thing. Because these are going to be all over the place, we can sort our rows, like we can sort each row. And let's think about how we'd want to sort the row. So let's maybe look at this like bottom row first. How would we want to sort the row? And the reason we can sort the row is because when we find, like let's say the biggest rectangle we can make in this whole grid is this one. If we have something like, let's actually go back to this example here. And this is going to make it a lot clearer. So let's say this is already sorted. If we have 1, and then we have 2 here, and we have 1, 2, 3, like this, then we know that here we have 3, and here we have 2. So we know that like if these two are together, we can easily make a 2x2, right? We're going to take the minimum of these and make something. But how do we want to sort these efficiently to make sure that like we get the biggest rectangle possible? And the way you're going to want to sort these is in descending order. Because, like looking at this picture, let's say, what if our biggest rectangle is actually just the first column? If we sort it in descending order, we're basically going to be checking every single area, and we're going to take the greatest numbers first, right? So like if we have numbers like this, like 5, 4, 3, 2, 1, we will check a 1 by 5, and then a 2 by 4, and then a 3 by 3, and so on. Where if we had it another way, it would be a lot worse, right? Like if we had it like this, then how would this even work, right? Like we wouldn't want to use this. We want to use the biggest side available first, basically, right? We want to use the biggest side available first, and then as we extend it to be more and more area, then we just see like what's available after that. So we're going to sort every single row from increasing to decreasing order. So let's do that as well, and then let's have some kind of result. And this is going to make a lot more sense. So let's have a result. Let's just set it to 0. So let's sort this top row first. So it'll just be 1, 1, 1, 1, 0. And then obviously these have an index, right? So we can go down the row and we could say like, okay, well, if the bottom right corner of our rectangle is this square, how wide is this? Well, this is only 1. And how wide is it? It's only 1. It's 1 up and only 1 across. So this would be a 1 by 1. So our result here would be updated to 1. Now, what if this was the bottom right? Then anything to the left of it would also be included, right? Because we are doing it in descending order. So we would have a 2 by 1 because we have 2 numbers now. So we can get a 2 by 1 if this was the bottom right. If this was the bottom right, we'd have a 3 by 1, right? 3 by 1. If this was the bottom right, we'd have a 4 by 1. And this is going to make a lot more sense with the bigger numbers as well. So the biggest thing here we can make is a 4 by 1. And obviously with a 0, it would just be 0. So the biggest rectangle we can make with this top row is a 4 by 1. So we will update our result to be 4. Now let's sort this again. So if we have 2, 2, 1, 0, 0, let's see what happens here. So in the first row, we have 2 squares. So if we just use this column only, we can build a 2 by 1, right? We only have 1 column, so we can build a 2 by 1, which would be 2. But that's not as big as our previous one. What about over here? So here we have a 2 as well. And remember, we can use every row before this because every row before this is greater than or equal to this number. So if every row before this is greater than or equal to this number, that means whatever row we're on, that will be the height of our rectangle. And then the width will just be the number of rows we've traversed. Right? So we can write that down as well. So cur is height, and then width equals number of rows we've traversed. Or I guess if you want to use an index as well, this will be the index plus 1, right? So if this was like index 1, we'd have 2 here. And then we basically just multiply both of those, right? The height by the width to get the rectangle. So here we can get a rectangle of 4, and that makes total sense, right? Because if we go back to this, we can easily make a 2 by 2 because the way it would work is we would take this one over here, because after we sorted, we would put this column right over here, right? And then we would get something like this, where we would get a 1, 2, 1, 2, because we have 2 of them. So this basically means this whole grid is by 1s, right? Because remember, 2 means there is 2 1s in a row. So it would basically be like this. So that's why we know we can do that. So let's go keep going here. The next number is 1. That means the height is going to be 1, and the width will be how many we've traversed. So this is 3. So this is going to be a 3 by 1, which is still smaller than our result. And this also makes sense, right? We could easily build a 3 by 1 here if we just have these 2 and these 3 columns right next to each other, right? So we could have like these 2 and then this one or whatever. Or if we wanted this one to be the third one, we could have this one, then this one, then this one, and so on. Okay, so let's go. And now we have a 0, so anything with zeros will just give you a 0 error, right? So we can keep going. So for the next one, we get 3 sorted again, 2, 1. So now 3 means we're on the first one again. So we could build a 1 by 3, right? And here we could build a 2 by 2, which is the same as we had before. And hopefully now you could see how you could build a 2 by 2. So there's a few ways you could build a 2 by 2. You basically can't build anything more than a 2 by 2 because if you look, any of these numbers always has a 0, right? So this column has a 0 here, this column has a 0 here, and this is the only one that has everything. So you would just take this column and you would take this column here, and that would build a 2 by 2, right? It would be like this, and this would give you a 2 by 2. And this is a 1 by 0, or sorry, this is a 3 by 1, which are all smaller than the result so far. So these are all zeros, so we don't really care about any of those. So let's go to the next row. So we have 4, 3, 2, 1, 0. Okay, and now we're going to be able to build some bigger rectangles here. So for this first one, we can build a 4 by 1, which is the same. But now for the second one, now we have a 3 by 2, right? So this is going to be 6. So that's better than what we had before. So we have 6 here. Then here we have a 2 by 3, which is 6 as well. And finally here we have a 4 by 1. And let's take a look where we would be able to build a 3 by 6. So it would be in the order of, this would be column 1. This, or sorry, this, how we build a square of area 6, or a rectangle with area 6. This would be column 1, this would be column 2, this would be column 3. And let's take a look. And indeed, we do have 3 things, right? So we have this and this. These are all 1s. So anything bigger than a 1 is just a sequence of 1s. So these are all 1s. So we can just put these 3 columns together, and now we'd have a rectangle with area 6. So notice how sorting immediately gets us, like, we can keep getting rectangles, and we can keep going down and getting them. So it's very convenient. So let's go for the last one. So we have 5, 3, 2, 0, 0. So here we can build a 1 by 5, smaller than our result. Here we can build a 2 by 3, same as our result. And finally here we can build a 3 by 2, same as our result. So the biggest rectangle we can make here is a 3 or a 6 area rectangle. And that is indeed the case. So there's a bunch of them, right? There's like this one with this. If we put these together, there is another one over here, I believe, right? Actually, I don't think there's one over here. Is there one over here? No. Oh yeah, there's this one over here. Right, so if we put these together and so on. So these are like our biggest rectangles. We can't build anything more than a 3 by 2. And indeed, you can see that like if we try to use these, there's nothing else in here because this is 0, there's 0 here, 0 here, 0 here. Right, so this is the biggest thing we can make. And so all we had to do was make a list, right, of increasing 1s, and that tells us for a particular cell how many 1s are there, and then we can use that information to figure out what's the actual area of our rectangle by sorting these in a decreasing order, and then from that we could figure out like exactly, we're essentially doing a greedy area calculation, right? Where we're just going to say, okay, we're going to take the ones with the biggest number first, and as we extend out our width, we will take smaller and smaller ones, and then we'll figure out whatever gives us the biggest area. So now we have enough to code it up. So let's do that. So we are going to have a rows and columns. It's going to be a length of the matrix and length of the first row. Then we're going to have the squares that we're going to calculate all our numbers. So we'll say squares. So for the first row, we will just copy the first row of the matrix because every row relies on 1s from the above row, so we don't want to be out of bounds. So we could just say like squares equals matrix 0, the first row, and then from there we will just initialize everything to 0, and then we will loop through all of these values to actually fill them out. So the first row is going to be straight out of the matrix, and the rest of them will just initialize to 0, and we'll actually loop through to fill them out. So we'll say 0 times calls for, we don't need this value, in range 1 rows, right? Basically going to get a new row for the rest of it, filled with zeros. And we'll make a result, and we'll set it equal to 0. So now we actually have to go through this empty squares and fill it out with our values from our actual list here, right? We have, like, this one we got straight out of the matrix because it is basically straight out of the matrix, right? If there's a 1 in the matrix, there's a 1 here. If there's 0, there's a 0 here. But this we initialize to 0, so this we do have to loop through our code to get it. So let's do that. So we'll say for row in range 1 rows. Remember, row 0 is straight out of the matrix, so we didn't do that. We need to do the rest. For call in range calls. And basically, if it's 0 in the matrix, then it's going to be 0 in our squares. But if it's non-zero in the matrix, then we need to add 1 to the number above it. So we'll say if matrix row call equals 1. If it's 0, we don't have to do anything. We'll just leave it at 0. Then here we need to do squares row call equals the one above it. So squares row minus 1, right? That's going to be the row above it, and the column is going to be the same. We'll just add 1. Now what we have to do is for every single row in squares, we have to sort it in decreasing order, and then we have to calculate our areas for every single possible as we go down, right? We'll start with the biggest number, and then we'll keep going down, and it's going to be the length times the width. So for row in squares, row.sort, and we want to sort it in reverse order. And then what we want to do is we want to go through the row and actually calculate the area. So for I can arrange columns, we want to calculate our area and maximize it with a result. So we'll say res equals max, the old result, and it's going to be the actual value here. So remember, the value here is the height, and then I plus 1 is the width. Right? So if we're on like I equals 0, then the width will be 1 and the height will be the actual value. So this is I plus 1. So now that we maximize our result, we can just return it. And that. And accepted. And there you go. So it's pretty efficient. So let's go through the time and space for this one. So for the time, what are we doing? So we are creating the squares, which is already m by n. And then, or we call this like row times columns to make it easier. So row times columns. Now this is also a m by n, and we are sorting every single row. Right, so we're basically sorting the entire, we're sorting every row, so that would be like, let's see, for the row, it has C columns, right? So it would be like, how many rows are we sorting? We're sorting our rows, and then the number of columns would be like R, it could be like this, R log C, something like this, right? We're doing it R times, and then the number of items we're sorting in each row is C. So I think it's something like this. Yeah, for every column to sort a column, it would be, actually, I think it would be C, no, I think it would be like this. It would be RC log C, actually. So this term is basically out of it now, right? Yeah, because to sort a column, it would be n log n. So this is basically sorting like if you want to sort like an array of n. So every column is C log C, and then yeah, we do that R number of times. So it's RC log C as our final time here, where R is rows and C is columns. Okay, and for the space, so this is just RC. Oh, yeah, this is RC because we did make a new squares array or a new squares matrix. You could do this in place, but generally you don't really want to be doing stuff in place for input unless they like, tell you to do it. So I don't think you can do any better than this. So yeah, I think it's going to be this. And yeah, so definitely kind of a weird problem, but once you realize that all you need to know is just for every single cell, what's the biggest square I can make with that cell, then it becomes a lot more intuitive. And so that's going to be all for this one. Hopefully you liked it, and if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.